Ladies and gentlemen, the title of this talk is Robust Sample Budget Allocation for Multiple Importance Sampling. Rendering means the integration of the contribution of those light paths that connect the light sources to the camera through a pixel. As a light path is defined by an arbitrarily long sequence of visited points, this is a high, in theory, infinite dimensional integral. Monte Carlo methods offer a feasible approach to estimate such high-dimensional integrals, which uses randomly generated light paths and obtains the estimate as the average of the ratios of the transported radiance and the probability density of the light path sample. According to the concept of importance sampling, it is worth using probability densities that are at least approximately proportional to the integrand. The intuitive explanation is that in this case, the ratios will be close to constant, thus the average will have only small fluctuations. However, if the density does not follow the integrand, then there will be regions where the integrand is large, but the probability density is small. Such regions are rarely sampled, but when we are lucky enough to generate a sample here, a huge integrand per probability density ratio is added to the estimator. Thus the estimates are smaller than the real value for a longer time, then they make a huge increase, which introduces significant noise and supernova-like artifacts in the image. An appropriate probability density should not only mimic the integrand, but should also provide easy sample generation, for example by transforming uniformly distributed samples, which often contradicts to the requirement of being similar to the integrand. A successful compromise is the concept of multiple importance sampling, which uses a mixture of probability densities, where each density is good for easy sample generation, but typically fails to mimic the integrand alone. However, by approximately mixing several densities, the approximate proportionality can also be satisfied. Then the crucial decision is the weighting scheme of such a mixture, or the allocation of the total sample budget for individual sampling schemes. This weighting scheme is defined by variable alpha when only two densities are mixed. Intuitively, we wish to maximize the image accuracy, for which we need to maximize the similarity of the integrand and the mixture probability density. This seems straightforward, but what is the exact measure of the similarity between the integrand and the probability density? In this paper, we investigate this problem. Multiple importance sampling and its balance heuristics were introduced to computer graphics by Veach. It has very many applications and generated a lot of follow-up papers, so we can concentrate only on the most relevant ones from the point of view of our contribution. Veach also proposed to give equal sample budget to each combined technique, stating that other techniques can only be slightly better. This was proven wrong, and Sbert², Laszlo² and also Havram proposed heuristics for the sample allocation with more significant variance reduction. Warba and Müller proposed the consideration of the more stable Kullback-Leibler divergence instead of the variance during the optimization, and Müller and Murray also used neural networks for the optimal sample budget allocation. Kondapaneni, Sbert² and Elvira also investigated the theoretical optimum, but this leads to equations which require numerical methods. Generally, we can use the following scheme for optimal sample budget allocation. First, a dissimilarity functional must be defined that assigns a scalar value to the pair of functions including integrand f and probability density p. Here, d can compare their local values, and the integral is responsible for taking into account the whole domain. The control parameter alpha is included in the mixture density. Minimal integration error corresponds to the minimal dissimilarity. Thus, the derivative of the dissimilarity with respect to alpha must be made equal to 0. As the mixture density depends on the control parameter linearly, this condition can always be rewritten in the form expressing the fact that the expectation of the derivative of d with respect to density p must be constant for different sampling methods, which is an equation expressing the optimality. This equation can be solved by efficient Newton-Raphson iteration. In rendering, neither integrand f nor difference d is available analytically, so we can only evaluate them in discrete samples. Thus, the parameters of the equation of the optimality need to be also estimated from a typically low number of random samples taken previously in order not to introduce too high overhead. These estimates have some error, which may modify our choice aiming at the optimality. Thus, when appropriate measures are searched, the robustness of their estimates should also be taken into consideration. This observation leads to the motivation that the general solution process is traversed in the reverse order. Instead of first defining the dissimilarity and obtaining an equation of optimality where the parameters are hard to find, we start with heuristic establishment of the invariant, that is the equation of the optimality, with the objective of robust parameter estimation, and go backward to check whether the resulting dissimilarity measure makes sense. Our heuristics is fairly simple. We require the expectation of the ratio of the integrand and the mixture density to be invariant for the selection of the sampling method. First of all, it makes sense, since when the mixture density is exactly proportional to the integrand, the ratio is equal to the integral, so the expectation value is also equal to the integral no matter how samples are generated. Moreover, if the mixture density is at least approximately proportional to the integrand, the ratios have small fluctuation, so the parameters of the equation of optimality can be estimated from a very few samples. Our heuristics is further justified by the expression of the corresponding dissimilarity measure, which can be obtained by integration. This is the cross entropy between the integrand and the mixture density, which is a widely accepted functional in statistics. To demonstrate the merits of the proposed heuristics, we take the classical scene of Veitch, where spherical light sources of different sizes illuminate rectangular surfaces of increasing specularity. Light source sampling is good for small light sources, but fails at highly specular surfaces. On the other hand, BRDF sampling handles highly specular surfaces well, but is poor to simulate small light sources. Equal sample budget multiple important sampling combines the advantages of both techniques. The question is whether or not we can do it even better with non-equal sample budget allocation. We have compared equal sample budget multiple important sampling, considering it as a reference, and the relevant previous work with our new proposal. Note that there is room for close to 20% improvement. Liu et al. Used Taylor's approximation of the variance around the equal budget case and solved the resulting equation for the weight. Sbert et al. Also optimized the variance but with an iterative Newton-Raphson solver. Müller et al. Optimized the Kullback-Leibler divergence instead of the variance with the Adams version of gradient search. Furthermore, instead of executing the search in the unit interval, they mapped the unit interval to the whole number line with the sigmoid function, thus handled the interval boundaries in a better way, or replaced the originally constrained optimization with an unconstrained one. And finally, our method solves the requirement that the expectations of the integrand per the density must be independent of the sampling method, which is equivalent to the optimization of the cross entropy. So as a conclusion, this paper proposed a heuristics to find the quasi-optimal budget allocation in multiple important sampling. This heuristics aims at the equality of the expectation of the ratios of the integrand and the combined density when samples are generated with each particular sampling method. Thank you for your attention.